Educational videos by MMS programs. Chapter 1, Basic Design Concept. The purpose of structural design is to design a structure for adequate safety, adequate serviceability, and economy for its intended life. Adequate safety. The structure should be capable to sustain the desired loads, overturning, sliding, buckling, fatigue, or fracture for the intended life of the structure, so that the possibility of for the so the possibility of the collapse are very low. Okay. Adequate serviceability. The structure should perform satisfactorily under the service load without any discomfort due to excessive deflection, visible cracks, and vibrations. Right. Other conditions that come under serviceability are durability, impermeability, acoustics, thermal insulation. Important definitions. Service load, also known as working loads. These are the loads which are subjected to a structure in its day-to-day intended life. It does not include any accidental overloading or safety factor. The ultimate loads, okay, they are also known as collapse loads. These are the maximum load which the structure can carry before failure, right? Types of design methods. Working stress method this is the oldest design method. It was used around about 100 years for 100 years. It was used for RCC structure, steel structure, even for timbers, right? Okay. The important assumption in this method that the design stress strain curve is linear. Okay. Design stress strain design stress strain curve is linear. Okay. The structural material is assumed to behave in a linear elastic manner. For satisfying this assumption, the specified permissible stresses are kept well below the material strength. That is, for example, say you have concrete grade M25, then its characteristic strength is 25 Newton per mm square. But in case of working stress method, the permissible stress for M25 is taken as 8.5. That is, we are reducing the strength by 3 times, right? This method gives large section. So when the sections are large, so there will be less deflection and the cracks will be small, okay, which satisfies the serviceability criteria. This method gives very conservative and uneconomical design, right? Okay. Now comes ultimate load method. The assumed design stress strain curve is non-linear. This is non-linear. The ultimate load method makes it possible for different types of load to be assigned for different load factors under the combined loading condition. That means you can apply different load factors to dead load, live load, wind load, earthquake load, and you can also form different load combinations, after which you have to form an envelope and take the maximum moment and shear for which the structure has to be designed. The design section obtained by this method are small and slender and does not guarantee the satisfactory serviceability performance. Okay, as the sections obtained by this method are small and slender, they may not uh, give a deflection. Okay, or you can say they may not give sections which will satisfy the deflection and crack fit criteria, right? In the normal service loads, right? Okay. Limit state method. LSM aims for a comprehensive and rational solution to the design problem by considering the limit state of collapse at the ultimate loads and limit state of serviceability at the working loads. The LSM philosophy uses multiple safety factor format which attempts to provide adequate safety at the ultimate load as well as the adequate serviceability at the working loads. Okay. So design stress strain curve as per IS 456 2000 in flexure compression is this. Okay. This is given in the code. This blue line is the neutral axis and this XU is the depth of the neutral axis. At neutral axis, the strain and the stress are zero. Okay, we'll study this in detail as we move further. Okay, right. Okay, okay, fine. Core recommendation for limit state design. Characteristic load is defined as the load that has a 95% probability of not being exceeded during the lifetime of the structure. Okay, 95% probability of not being exceeded during the lifetime of the structure. Very important. Okay, this definition is given in clause 36.2 of IS 456 2000. The value of dead load, live load, wind load, snow load can be taken from IS 875, part 1, part 2, part 3, part 4, and value of seismic load can be taken from IS 1893. Design load is obtained by multiplying a appropriate factor to the safety. Appro uh, Design load is obtained by multiplying appropriate factor of safety to the characteristic load. Characteristic load, right? Partial, sorry, partial safety factor for loads, lambda is, okay. When the characteristic load is multiplied by partial safety factor of load, we get the ultimate load, for which is also known as factor load, and for this factor load the structure has to be designed. The partial safety factor to be used for calculation, the factor loads as per IS 456 2000 are given in this table below. So this is a table which is given in IS 456. These are different load combinations. This is ultimate limit state, in which we apply different load factors to dead load, live load, wind load, and earthquake load. And this is serviceability limit state. Here usually load factor of unit is multiplied. Over here we can see a zero point 0.8, and zero point 0.8 is multiplied with live load and earthquake load, right? Characteristic strength of material is defined as the strength of the material below which not more than 5% of the test results are expected to fall. Okay. In case of concrete, we make cubes in laboratory, and then we test the compressive strength of the cube on the UTM machine. And in case of steel, we take 1 meter bar length, and again we test its strength on the UTM machine, right? So the for concrete, okay, a characteristic strength of concrete is the strength of concrete specimens, that is cube, casted and tested as per given code of practice, and cured for 28 days. 95% of the tested cube should not have a value less than this values, right? Say suppose you are testing a cube which is made of M25 grade concrete. You're testing say 10 cubes, then out of 10, 95% of the cubes should give your compressive strength more than or equal to 25 Newton per mm square. Okay. Similarly, when 1 meter steel bar are tested on UTM, then 95% of tested bar should not have stress value less than its characteristic strength Fy, right? Okay, very important. Okay, uh, design strength of material. Okay, design strength of material is obtained by dividing the characteristic strength of material by approved partial appropriate sorry by appropriate partial safety of factor. For concrete, the partial safety of factor to be taken is 1.5, and for steel the partial safety factor to be taken is 1.15. That is in case for ultimate limit state, that is limit state of collapse, right? So I am showing three graphs over here. Okay, the first graph shows the characteristic strength of cube. Second graph shows the characteristic strength for concrete, and this third graph shows the design strength, design curve. Okay, so FCK is the characteristic strength for a cube. A cube is prepared in laboratory with extra care, and the load is applied on the cube for a very short period. But actual concrete is a huge mass, is is a huge mass of concrete, okay, and the loading applied on the actual structure is for the lifetime, right? And you can see that at different sections the strength of the concrete also varies because it is in situ concrete. For that reason, the code has reduced this strength by one third, okay, and so we are taking the characteristic strength of concrete as 0.67 FCK. Now, when you divide this characteristic strength by the partial safety factor for concrete, that is 1.5, you get the design strength, that is 0.447 FCK. Okay, fine. Okay, for concrete, the partial safety factor to be taken is 1, and for steel, partial safety factor to be taken is 1 for serviceability limits. Okay, this is for serviceability limits. Okay, because we are interested in finding the actual deflection, actual crack width for the actual loads. Okay, this calculation require the computation of stresses under service loads, and moreover this calculation perform a part of the working stress method. Okay, so when you are doing limit state of serviceability, in that case you are going to use this stress strain diagram. Okay, the important assumption, this is the stress strain diagram for working stress method. Okay, the important assumption in this method is that the design stress strain curve is linear. The structure material is assumed to be to behave in a linear elastic manner. Okay, for satisfying this assumption, the specified permissible stresses are kept well below the material strength. That is what we have understood above, right? So for doing the check for serviceability, you will use the permissible stresses that are given in case of working stress method. Say if you want to do the check for deflection for this beam. Okay, so this is a compressive strength of concrete in bending, this is tensile strength of concrete in bending, this is sigma cbc, this is sigma cbt. Okay, and say this is a beam in direct tension. So if you want to do the check for deflection, then permissible stresses in concrete for strength design, you would use this. Bending compression sigma cbc, it is 8.5 and 10 for M25 and M30. For direct compression, it is 6 and 8. If you want to do the check for crack width, then bending tensile stress is 1.8 and 2 for M25 and M30, and direct tensile stress it is 1.3 and 1.5, right? Okay, so these are the stresses, okay, which you have to use, right? The modular ratio M, that is, this is the empirical formula for given in working stress method, 280 by 3 sigma CBC, considering the long-term effect of creep. Okay, but for simple transform section, the modular ratio is taken as ES by EC, where ES is the modulus of elasticity of steel, and EC is the modulus of elasticity for concrete, right? Permissible stresses in HYSD bar for strength calculation, okay, that is according to WSL. Bar in tension, bending and shear is 130 Newton per mm square. Bar in compression is 140 Newton per mm square. Okay. Design stress strain curve for concrete in flexure compression. So this is the detailed graph shown over here. First, strain varying from 0 to 0.002, 0 to 0.002 strain. Okay, this is strain, this is stress. This stress strain curve is parabolic. Okay, this is parabolic, right? For strain greater than equal to 0.02, the stress remains constant, that is 0.447 FCK. From further over here, if the strain is increased, okay, the stress remains constant. Okay, so in this region, this is the ultimate, you can say, the design stress, that is 0.447 FCK. This is what we got from here. Okay, that is 0.67 FCK divided by 1.5, that is equal to 0.447 FCK. Okay, okay, and if you want to find the stress in this parabolic region, say you have a strain X and you want to find the corresponding stress in the concrete, in that concrete fiber, then put the value of strain over here and you will get Fc for the corresponding strain, right? Okay. Now, over here we saw that the design curve given in the code is something like this, right? Right. So that is how, which I have explained over here. Okay. When you turn this by 90 degrees, you get the graph like this. Okay. So this is strain, this is stress. Okay. The height of this parabolic portion is 4 by 7 xu and the remaining is 3 by 7 xu. Okay. So let me show you in the drawing above. Okay, what is xu? Xu is the depth of the neutral axis. This is xu. The height of this parabolic portion is 4 by 7 xu. Then height of this rectangular is 3 by 7 xu, right? So this is how this design curve has been given in the code. Okay, this is your design stress 0.447 fck. Okay, and the force C falls at a distance 0.416 xu from the highly compressed phase. Okay, this is force C falls at the CG of this uh, diagram, and that is 0.416 xu. Okay, fine. Okay, now it is assumed that the section of a flexure member fails by crushing of concrete and not by yielding of steel. Okay, when the concrete reaches the ultimate strain 0.0035, then it is assumed that the concrete will crush. Okay, the short-term modulus of elasticity of concrete is taken as EC is equal to 5000 into under root F. Okay, this is a short-term modulus of elasticity because uh, the long-term effect due to creep, shrinkage, and temperature are ignored, right? Okay, fine. Now, when the concrete is subjected to uniform compression, as in case of concentrically loaded short column, the ultimate strain is limited to 0.002 and the stress 0.447 fck is uniformly distributed over the whole section. Okay, so if you have a concrete section which is under pure compression, okay, in that case the ultimate strain is taken as 0.002. It is assumed that after that the concrete will crush, right? In case of flexure it was 0.0035, but in case of pure compression it is 0.002, and at this strain the stress will be 0.447 fck, which will be uniformly distributed over the whole concrete section. Okay, so this is the stress diagram, this is the strain diagram for uh, concrete under pure compression. Okay, and this is for flexure. Okay, compression in flexure, right? Okay, in case of concentrically loaded short column which is under pure compression, the neutral axis will be at infinity. Okay, that is why you have uniform strain, uniform strain and uniform stress over the whole section, right? Okay. Okay, when the concrete is subjected to both axial compression and flexure, the ultimate strain is limited to a value between 0.002 to 0.0035. Very important, right? So such cases rarely occurs on practical field. All the columns, or you can say, that are usually biaxial columns. Okay, so when the concrete is subjected to axial compression and flexure both, right? So this is the first case. Okay, when the neutral axis depth falls in the concrete section, then the strain, the ultimate strain for the concrete is taken as 0.0035, and this is the corresponding strain in the on the tensile phase, right? The design stress strain curve to be followed for this section is this. Okay, you have to follow this design curve, right? Okay, now when the neutral axis falls outside the concrete section, okay, and then this is your D. Okay, and then this strain will vary between 0.0035 and 0.002. Okay, so this is the strain diagram shown over here, and this is the pivot, and which is at a distance 3 by 7 D. Okay, the strain over here will remain constant 0.002. If I move this neutral axis further, then this strain will reduce, this strain will increase. Okay, EU is the least strain. So this strain diagram is shown over here. As the neutral axis is outside the section, concrete section, so you will have a stress, design stress like this something. Okay, this is 0.447 FCK, but code says that you can take an average stress diagram. Instead of 4.447 FCK, you can take it as X FCK. X you have to find. First find G. You know XU, you know D, you can find G. Once you know G, you can find X. Once you know X, you can find J. Okay, J is the distance at which this force false, right? So this is how you can take the average stress diagram. This is very important. Okay, all the students should understand this fundamentals very thoroughly. Okay. Okay. Now, when the concrete is under pure compression, we know the neutral axis will be at infinity and the ultimate strain will be 0.002, and for this your stress will be 0.447 FCK. So these are different cases which you will have to use as according to the depth of the neutral axis. Okay, so this is very important. Design stress strain curve for mild steel. Okay, Fe 250. The characteristic strength is 250 Newton per mm square. Design yield strength of mild steel FYD is characteristic strength divided by partial factor of safety, that is 1.15 for steel, that is equal to 0.87 F5, right? Okay, fine. This is the graph. Okay, this is the design, this is the characteristic curve for mild steel, and this is the design curve FID for the mild steel. Okay, the modulus of elasticity for all grade of steel is same, that is ES is equal to 200,000 Newton per mm square. As according to IS 456, the modulus of elasticity for steel in tension zone and compression zone are to be taken same. Very important point. Okay. In case of mild steel, which has well-defined yield point, the behavior is assumed to be perfectly linearly elastic up to a design stress level FID 0.87 F5. Okay, so this is linear. Okay, and the corresponding yield strain is found by this formula 0.87 F5 by ES, that is equal to 0.0010875. Okay. Okay. Now, design stress strain curve for cold work bars. Okay, for Fe 415, characteristic strength F5 is 415. For Fe 500, characteristic strength that is F5 is 500. And design yield strength, this is sorry, mistake. It is HYSD bar. You can, or you can take cold work bars. Okay, might not match. Fi divided by the factor of safety, that is 1.15, that is equal to 0.87 Fy. Okay, so this is the design curve for Fe415. Okay, and this is the design curve for Fe500, right? So we can see over here that the graph varies linearly. The stress strain graph varies linearly up to this point, and this at this point the stress level is 0.8 FYD. Okay, FYD is the design strength, that is 0.8 into 0.87 into 415, that is for Fe415, and this is for Fe500, that is 0.8 into FID, that is 0.8 into 0.87 into 500, right? Fine. Uh, Cold work bars do not have a specific yield point. The full design yield strength of 0.87 Fi is assumed to correspond to a proof strain of 0.002, and the yield strain is taken as 0.002 plus 87 Fi by ES. Okay, very simple. So over here, in case of cold bars, there is no specific yield point. So what we do, we take a proof strain of 0.002, we draw a line parallel to this line, and wherever it cuts the graph, this point we assume that the steel reaches the yield stress, that is 0.87 F5, 0.87 F5. This is for 500, this is for Fe5, this for Fe500, this is for Fe415, right? Now we can see between these 2 points, the graph is not linear, right? Okay. So code has divided this part into 5 segments, 5 linear segments, you can say. Okay. And the silent features for this are given. Okay. in this table. When stress is zero, when stress is zero, strain is zero. Okay, strain is zero, stress is zero. Okay, we are taking for Fe415. When strain is 0.00144, the corresponding stress is 288.8. Okay, when your strain is 0.00163, the corresponding stress is 306.9. Okay, 306.9, and so on. This is 0.0038, and you get the yield stress. Okay, that is 361.05. Okay, so this is how this uh, design curve can be understood. If you want to find the stress in between this linear segments, then you can do the uh, linear interpolation. Okay, so that is very easy. So these are the silent design stress corresponding to any can be obtained by linear interpolation. That is what I explained. Some if the strain is in between the segment, then you can find it by interpolation, right? So this is the table for Fe415. This is a table for Fe500. Okay. The above table is valid for steel in compression zone and steel in tension zone. Okay. This table is valid for both compression steel and tension steel, right? And this design curve is also valid for both, that is steel in tension and steel in compression. Okay, so this video is very important. Okay, it is very necessary for all the students to understand these fundamentals thoroughly. Okay, I hope I have made this video useful for you. Okay, please visit website mmsprogramcivil.com, where all the education videos are uploaded. Thank you.